Okay, so you look at your magnetic field worksheet. The first question that you can have a look at is actually page 11. Okay, so have a look at page 11, November 2016 P42. Okay, they mentioned to you that you have a stiff wire that is held horizontally between the poles of a magnet as illustrated. When a constant current of 6 amps is passed through the wire, there is an additional downward force on the magnet of 0.08 Newton. On the figure, draw an arrow on the wire to show the direction of the current in the wire and explain your answer there. So right now, take note of what the question mentioned. They mentioned to you that you have a downwards force on the magnet of 0.08 Newton. So there is actually a force acting on the magnet right now. That force is actually downwards. This is the FB acting downwards on the magnet itself. Okay, but the question wants you to work out the current direction inside the wire itself. That wire being this wire here. Okay, so how do you start off with determining the direction of the current inside the wire in the first place? Now, if you know that the direction of your magnetic force on the magnet is downwards, according to Newton's third law, the direction of magnetic force on your wire should be upwards. There should be an equal opposite magnetic force acting on your wire right now. So this is the FB on your wire. This is a consequence of Newton's third law. All right. So now that you have the direction of your magnetic force, is there any other thing that you also know? Notice that this is your north and south pole. So if it's north and south pole here, that means that the direction of your magnetic field will be in this direction. Okay. It's always from north to south. Now that you know your magnetic force direction as well as your magnetic field direction, you can now then work out your current direction. If you refer back to your Fleming's left-hand rule, this one is the poorly drawn example of it, but you get the idea. This one is your magnetic force. The thumb is your magnetic force. The index finger is your magnetic field. The middle finger is your current. So if you orientate your fingers accordingly, following what you have in the question, make sure you align your thumb to follow the direction of the magnetic force, your index finger following the direction of the magnetic field. You will notice that your middle finger is pointing in the direction of the current. So the direction of your current is supposed to be in this direction here. Okay, so just draw an arrow to indicate the direction of your current on the diagram itself, but you still need to explain your answer. So how you explain it is through something like this. Since force acting on the magnet is downwards, according to Newton's third law, there will be an equal opposite force that is acting upwards on the wire. And according to Fleming's left-hand rule, the direction of the current now should be from left to right, as shown in the diagram above. Okay, so that's for that particular question here. Part B, you cannot do yet because this one is related to alternating current. So we'll leave this one for now until we go through the portion related to alternating current. So this is one question here. Okay, for the next question, let's look at page 34. This will be March 2019 P42. In this current question, you have a horseshoe magnet that is placed on a top band balance. A rigid copper wire is fixed between the poles of the magnet as illustrated in the figure below. The wire is clamped at ends A and B. And then for the first part, when the direct current is switched on in the wire, the reading on the balance is seen to decrease. From there, state and explain the direction of number 1, the force acting on the wire, and number 2, the current in the wire. Notice that the situation that's described here is actually closely related to what you've learned in the notes. So let's recall a bit of what we learned. If you have a magnet like this that is actually resting on your top band balance, like this. Firstly, if we say that the reading is increasing, that would have meant that something is actually pushing down on the magnet itself. which in turn causes the reading to increase. So the force on the magnet right now is acting downwards. But in your current case, there's actually two separate objects to consider, the magnet as well as the wire. So the wire is actually in the middle right over here. So if you already know that the force acting on the magnet is downwards, it follows that the force acting on the wire must be upwards now, because this must be following Newton's third law, which states that when two objects interact, they will be equal and opposite forces exerted. Okay, so in your case, when reading increases, the force on the wire must be upwards now. But now, what the question mentioned was that the reading is actually decreasing. So if you were then to try and look at what happens now when the reading is actually decreasing, let me just draw out again the magnet resting on your top band balance like this. If your reading was decreasing, that would have meant that there is a force acting upward on the magnet. It's trying to pull the magnet off the top band balance. That's why the reading is decreasing right now. So right now, if your wire is in the middle again, since the force on the magnet is outwards, according to Newton's third law, the force on the wire must therefore be acting downwards now. This would be the force acting on the wire. So this is the situation that has been described inside your question right now. Okay, so how would you actually word your answer? You could probably say something like this. Since the balance reading is decreasing, the force acting on the magnet is upwards. And according to Newton's third law, the force on the wire must be downwards now. Okay, so that's pretty straightforward. Then now, if I wanted to draw the forces on the existing diagram, the force acting on the magnet is actually upwards, since the reading is decreasing. But now, the force acting on the wire is going to be downwards, according to Newton's third law. So now, if you then want to predict the direction of the current inside the wire, you need to use Fleming's left-hand rule. So Fleming's left-hand rule, if you remember, looks something like this. Okay, where your thumb represents your magnetic force, your index finger represents your magnetic field, and then your middle finger represents your current. So one thing to note was that when you're talking about the direction of your magnetic field, it's always from the north to south pole. And then when you're talking about your current, it's always talking about the direction of your conventional current. So right now, if you notice that this one is north and this one is south, it follows that the direction of your magnetic field will be in this direction. So now, if you were to orientate your left hand according to the directions of the magnetic field and magnetic force indicated here, you ought to be able to determine that the current direction is actually going to be in this direction here. Okay, so now if you want to word out your answer, you just say, according to Fleming's left-hand rule, the current is flowing from B to A. Okay, then if you move on to the next question, under part B here, in the next page, you can just leave this question for now because this is relating to AC circuits from another different A2 chapter. So we'll revisit this question again once we have gone through your AC circuits. All right, let's move on to the next question. For the next question, you can actually have a look at page 41. This would be March 2020 P42. So in that question right now, for the first part, you are supposed to explain what is meant by a magnetic field. A magnetic field is just simply a region where a magnet, a magnetic material, moving charge, or current-carrying conductor experiences a force. Now in your marking scheme, you can actually just choose any one of these. But if you want to be safe, you can just write everything in. All right. Then if you move on to part B, the apparatus shown in figure 8.1 below is used in an experiment to find the magnetic flux density B between the poles of a horseshoe magnet. Assume that the magnetic field is uniform between the poles of the magnet and zero elsewhere, Notice that the diagram below here is actually quite similar to the one that you had before. The rigid metal rod of length 300 mm is fixed in position perpendicular to the direction of the magnetic field. The poles of the magnet are both 45 mm long. There is a current in the rod that causes a force on the rod, and the balance is used to determine the magnitude of the force. The variation with current I of the force F on the rod is shown in figure 8.2 in the next page. The magnitude of your magnetic force will be given by Fb equals to BIL. This one is under the condition that your wire is perpendicular to your B field. Alright. Now, if your magnetic flux density and length are constant, this would have meant to you that Fb is proportional to current, such that if your current increases, your magnetic force should be increasing. Okay, and then if you were then to compare the equation with the equation of a straight line, y equals to mx plus c, where y-axis is actually your magnetic force and your x-axis is actually your current, you could actually say that you will get a straight line passing through origin if Fb is plotted against current, which is actually what you have in the next page. So you look at the next page right now, this is the variation of your magnetic force with current. Okay, you're supposed to calculate the magnetic flux density B. Since the wire is placed perpendicular to your magnetic field, you could say that Fb equals to BIL. If we want to find out what is the flux density, we need to know the values of the other variables. When it comes to the values of your magnetic force and your current, you can actually use this graph straight away because this is a graph of variation of magnetic force with current. So you just pick any points on the graph for values of B and I. It can be this point here, it can be this point here, this point here, or even this point here. In my workings, I actually pick this point here, where your magnetic force is actually 9 millinewton and your current is actually 5 amps. Okay, so you have the value of magnetic force as well as current right now, but you're missing the value of your length. So remember that when you wanted to use this equation here, this length here is the length of wire in the magnetic field itself. It isn't necessarily the entire length of the wire. It just needs to be the length of the wire inside your magnetic field. So if you look at the diagram in the previous page, there are actually two different lengths. A 300 millimeter length followed by a 45 millimeter length. Since the length L that you want must be the length of the wire inside the magnetic field, it should be this 45 millimeter here. Because if you look at the diagram closely, this is actually the length L that we want, which turns out to be 45 millimeter. So if you were to take that value right now and to put it inside your equation, remember to change the 45 millimeter into meter, you multiply with 10 power minus 3. So from there, you can actually now get your magnetic flux density as 0.040 Tesla. Now, just be careful a bit about your final answer. If you have written your magnetic flux density as 0.04 Tesla, this one is really just 1 SF only. Most of the time, they don't accept your answers as 1 SF. Your answers must be minimum 2 SF and maximum 3 SF. Okay, just one thing to note. For the next question, let's have a look at page 23. This will be March 2018 P42. Under this question, You have a straight stiff wire that carries a constant current in a region of uniform magnetic flux density. The angle theta between the direction of the current and the direction of the magnetic field is varied. The maximum force on the wire is F0. On the figure below, show the variation in angle theta of the force F on the wire for values of theta between 0 and 90 degrees. Let's try to visualize what is being described by your question. You have a uniform magnetic field with flux density B that could probably look something like this. And then inside the magnetic field, you have a wire that is placed at an angle to the field. And inside the wire itself, you have current flowing through it, which makes an angle of theta to your magnetic field. In the previous lessons, you learned that the magnetic force acting on a wire that is placed at an angle to the field will be given by this equation. FB equals to BIL sine theta. You have constant current and a uniform magnetic flux density. You could also assume that the length of the wire inside the field is constant. So now you can say that B, I, and L are constant. Therefore, magnetic force is directly proportional to sine theta. Now, the significance of this relation here is that it will tell you that FB varies sinusoidally with your angle theta. It follows a sine function because of the sine theta that you have over here. If you then draw the graph of magnetic force variation with angle theta, it by right should look something like this. Okay, this is magnetic force, this is angle theta. Because the variation follows a sine function, you are going to get something that looks like this. Okay, so from the equation FB equals to BIL sine theta, you want to work out what is your minimum and maximum force. Your minimum force would be when the wire is parallel to your magnetic field. So your angle theta here will be 0. Your magnetic force will be 0. Okay. As for your maximum force, this occurs when your wire is perpendicular to your magnetic field. So your theta here will be 90 degrees and your magnetic force will be a maximum. In your current question is actually F0. Because the question already mentioned to you that the maximum force on the wire is F0. Okay, so right now on the graph, this one will be 0, and then this one will be F0. And recall that your question wanted you to only plot for values of theta between 0 and 90 degrees. So you're really only supposed to consider this part of your graph up to 90 degrees only. You will only be plotting the red highlighted section here. That's why your graph looks like this right now. You're only supposed to plot it up to 90 degrees from 0 to F0 only. Okay? Have a look at page 26 for the next question. This will be June 2018 P41. So for this question here, you have a rigid copper wire that is held horizontally between the pole pieces of two magnets as shown in the figure below. The width of each pole piece is 8.5 centimeter. The uniform magnetic flux density B in the region between the poles of the magnets is 3.7 millitesla and is 0 outside this region. The angle between the wire and the direction of the magnetic field is theta. And lastly, the current in the wire is in the direction shown in figure 9.1. Now, by reference to the side view of figure 9.1, which is actually this one, state and explain the direction of the force on the magnets. So they specifically want the magnetic force acting on the magnets right now. Now, since our magnet is north and south like this, the direction of our magnetic field would be in this direction here. And the question has already given us the direction of the current is going towards the right. So this would be the direction of your current I. Now you then use your Fleming's left hand rule where you say that your thumb your index finger and your middle finger are oriented 90 degrees to each other, your magnetic force being your thumb, your magnetic field being your index finger, and your current being your middle finger. If you orientate your fingers accordingly to the direction of current and your flux density here, you would see that your magnetic force is acting outwards. This is the magnetic force acting on the wire, but they want the magnetic force acting on the magnet. So according to Newton's third law, it should be acting downwards. This will be the magnetic force acting on the magnet. So how would you word your answer? You just say that by Fleming's left-hand rule, the magnetic force on the wire is acting upwards, and then by Newton's third law, the force on the magnet is acting downwards. Okay? As for the next part of the question, the constant current in the wire is 5.1 amp. For an angle of theta equals to 90 degrees, calculate the force on the wire. So since it's 90 degrees right now, you can imagine that if this is your magnetic flux density B in this direction, your wire is now placed at 90 degrees to the magnetic field. And your current is actually flowing in this particular direction right now, where the magnitude is 5.1 amps. So we already learned that if you're talking about the magnetic force acting on a wire perpendicular to your field, it's just going to be FB equals to BIL. So right now your B is going to be 3.7 millitesla, change out the milli. Your current is going to be 5.1 amps. And then lastly, your length. This one you need to be careful a bit. This one, as I mentioned to you, must be the length of the wire inside the magnetic field. So you look at the diagram that you had above, that length by right should have been this particular length here. This is the length that is inside the magnetic field and is actually the width of your pole piece. It will be 8.5 centimeter. So you just put in the value of 8.5 centimeter. Remember to change it out from centimeter. You will get your final answer as 1.6 times 10 power minus 3 Newton. Okay. Then you move on to part 2. The angle theta is now changed to 60 degrees. The length of the wire in the magnetic field is 8.5 over sine 60 degrees centimeter. Calculate the force on the wire right now. So since your wire is now placed at an angle to your magnetic field, it looks like this. All right. There's a certain angle that it makes with your magnetic field. So when it comes to the magnetic force acting on the wire, then we know that is FB equals to BIL sine theta. Your magnetic flux density remains 3.7 millitesla. Your current is 5.1 amps, but the length L that you would want to use right now is actually this one. They've already told you that the length of the wire inside the magnetic field is 8.5 over sine 60. Okay, and be careful with the units. Is in centimeter. You need to change it from centimeter to meter. Okay, and then what's left of the equation is that you just multiply with the angle, which is 60 degrees, so it's sine 60. Your final answer would thus be 1.6 times 10 power minus 3 Newton. Now notice that this answer is actually the same as the one that you had in the previous question. All right. So for some reason, even though your length is different here, that effect is actually cancelled off or offset by your angle. All right. Now for part C, you can't really do this question because this one relates to your AC circuits where they talk about frequency of current and then the root mean square value of your current. So we'll do this after we've gone through AC circuits. All right, then we move on to page 31. This would be November 2018 P42. So for this question, in the first part, you are supposed to define what is magnetic flux density. So remember that the magnetic flux density was actually defined from this particular equation, where you say that the force acting on a wire placed perpendicular to the field is actually BIL, and then the flux density is actually going to be FB over IL. Your flux density is actually defined from this equation. So when you define it out, you will call it as force per unit current in a wire of unit length which is perpendicular to the magnetic field. Okay, so the term perpendicular to the magnetic field is actually really important to be put in, because this equation here only applies for when your wire is perpendicular to the magnetic field. Okay, or you can also word it another different way: force per unit current per unit length of wire when current is normal to the magnetic field. Okay, either one works just as fine. As for the next part in B, you have a stiff copper wire that is balanced horizontally on the pivot as shown in the figure below. Sections PQ, QR, and RS of the wire are situated inside a uniform magnetic field of flux density B produced between the poles of a permanent magnet. The perpendicular distance of PQRS from the pivot is 7.5 centimeter. When a current of 2.7 amp is passed through the wire, a small mass of 45 milligram is placed at a distance of 8.8 centimeter from the pivot in order to restore the balance of the wire as shown in the figure below. This question is actually related to the current balance that we learned in the previous lesson. Let's first work out what are the magnetic forces acting on the wire, especially for the part of the wire that is between the pole pieces here of your magnet. So right now, you have current flowing in this particular direction for section RS, and then this direction for section QR, and finally this direction for section PQ. They never told you what are the polarities of the magnets used, but let's just assume that this one is north and this one is south, so that our magnetic field will be going in this particular direction here. All right, so then we work out what are the magnetic forces acting on each of the sections. Sections RS, sections QR, and finally sections PQ. To predict the direction of the magnetic force on each section of the wire, we will again rely on the Fleming's left-hand rule. You need again your 3 fingers here, your thumb being your magnetic force, your index finger being your magnetic field, and then your middle finger being your current. So if we analyze each section one by one, say maybe right now I say for section RS, the direction of my magnetic field is going to be like this, but the direction of my current is going to be like this. So if I then orientate my left hand according to Fleming's left hand rule, I would be able to work out the magnetic force as being in this particular direction here. This would be FRS, which is this one here. Okay. Then if I move on to the other opposite section, section PQ here, let's call this section PQ. The direction of my magnetic field is going to be like this, but the direction of my current is going to be outwards. So now if I were to orientate my left hand according to Fleming's left hand rule now, I ought to be getting a magnetic force that is actually pointing in this direction here. This would be my FPQ, which is this one here. Okay. Now notice that these two forces are actually opposite to each other, and because it was the same current and also the same length of wire that is inside the field, you could also say that the forces will be equal in magnitude too. So forces PQ and RS are actually equal and opposite to each other, but more on that later. All right, and then for our last section, section QR, we have our magnetic field pointing in this direction. We have our current going in this direction, and then according to Fleming's left-hand rule, our magnetic force by right should now be pointing downwards. This is FQR, which is this one over here. All right. For the forces on section PQ and RS just now, I had mentioned that the forces are going to be equal and opposite to each other. The reason is because you have the same current and length of wire inside the magnetic field. Okay. If you relate it to the magnetic force on a wire equation, FB equals to BIL. Since the current is the same, the length of the wire inside the field is the same, and you're also having the same flux density, it follows that your magnetic force will be the same too. Just that in our case, they are acting in opposite direction. That's why I could say that they are equal in magnitude, but opposite in direction. This would also mean then that your resultant force is actually zero in the horizontal direction. Okay, in the horizontal direction, you do not have any resultant force, but in the vertical direction, you actually have a resultant force in the form of the magnetic force acting on section QR. Now, if you were then to look at your wire balance from the front like this, it looks something like this right now. This one being your wire, and then this one here is your pivot. Your force QR is acting downwards like this. It's actually vertical. And then your forces PQ and RS would actually be acting right over here. This is force PQ and force RS, but they're acting in the horizontal direction. Okay, so right now, if you then look at what moments will be caused by the forces, force PQ and RS do not cause any moment because they're horizontal in the first place. There's no perpendicular distance between the forces to your pivot right over here. But when you're talking about force QR, there is actually a perpendicular distance between the force and the pivot. This one here being your perpendicular distance, it's actually going to cause a counterclockwise moment like this. So the question did mention to you that you actually attach some mass over at the other end in order to balance the entire wire. The weight here caused by the mass would actually cause a clockwise moment to balance the anti-clockwise moment caused by force QR. All right. So now let's have a look at the actual question itself. For section 1, you are supposed to explain why, when the current is switched on, the current in sections PQ and RS of the wire does not affect the balance of the wire. In other words, why doesn't it cause a movement of the wire about the pivot? We already discussed this at length just now, where I mentioned that the forces on PQ and RS due to the current are actually equal and opposite to each other. They cancel each other off. Hence, there is not going to be any resultant force or net force on the two sections. Therefore, you won't have any moments. You could also revert it another way by saying that the forces on PQ and RS are actually horizontal. There is no perpendicular distance between the forces and your pivot. Hence, they create no moment about the pivot. Okay? As for section 2, the length of section QR of the wire is 1.2 centimeter. Calculate the magnetic flux density B. This one, you will actually have to apply equilibrium to the wire balance, where you say clockwise movement equals to the anti-clockwise moments. But before that, you need to know the distances between the forces and your pivot. So if you refer back to the diagram from before, you had 7.5 centimeter between forces QR and your pivot. And then subsequently, you have 8.8 centimeter between your weight and your pivot. So that would have meant that here to here, you are going to have a distance of 7.5 centimeter, whereas from here to here, your distance is going to be 8.8 centimeter. So from here, you can then now apply your equilibrium conditions in order to solve the question. Now, if you look at the question itself, we know that the wire is balanced. This means that the sum of moments about any point must be equals to 0. In other words, clockwise moment must be equals to anti-clockwise moment. The diagram that you already have here is actually this same diagram here. Okay, so you look at that diagram, your magnetic force is the one that causes a counterclockwise moment, whereas your weight is the one that causes a clockwise moment. So right now, the moment caused by your magnetic force must be equal to the moment caused by your weight. So we know that moment in general is given as the product of force times perpendicular distance between the force and your pivot. So right now, we work out an equation from there. You can say that Fv times x1 is equals to W times x2. Your x here being the respective distance to the pivot for the forces. So right now, your magnetic force, I know you're talking about a magnetic force acting on a wire, so it must be Fb equals to BIL. As for the mass that you apply at the other end of the wire, it has a weight, so the weight will be given by W equals to mg. So this equation here, you go and expand it out, you will get BIL times x1 equals to mg times x2. Your x1 is actually 7.5 centimeter, your x2 is actually 8.8 centimeter. So all that's left for you is to put in all the values that you can get from the question. B is what you want to find. Your current is actually 2.7 amps. You can actually get it from the previous page. They already told you that you have a current of 2.7 amps here. Okay. And then after that, when you're talking about the length of your wire that is inside the field, it should be 1.2 times 10 power minus 2 meter. That is actually this length here. They told you the length of section QR of the wire is 1.2 centimeter. If you look at the diagram from before, this length QR here is actually the length of wire inside the magnetic field. So you use that value that is been given here, okay? And don't forget to change it out from centimeter. And your x1 here would be 7.5 centimeter. Again, change it out from centimeter. If you then look at the other side of your equation, you have the mass as 45 times 10 power minus 3 divided by 1,000. Now your mass is actually 45 milligrams. The question has already stated that to you. It's right over here. So if you were to change it out from milligrams to gram, it will be 45 times 10 power minus 3. But it will still be in grams. If you then wanted to change it to kg, you will have to take that 45 times 10 power minus 3 divided by 1,000 in order to change it to kg. That's the reason why right now your mass is written in this manner over here. Okay, so your gravitational acceleration remains as 9.81, and then your x2, which is a perpendicular distance, is 8.8 centimeter, change to meter. Finally, your answer will be 1.6 times 10 power minus 2 Tesla for the magnetic flux density. Okay, so that should be it for this question. For the next question, let's have a look at page 44. This is actually quite similar to the question that you just did under page 31. The current question will be June 2020 P41. In this question, you're supposed to define the Tesla. Now, the Tesla is actually the unit of magnetic flux density. We know that it was actually defined from this equation when you're talking about the magnetic force acting on a wire that was placed perpendicular to your magnetic field. Right now, your flux density is going to be your magnetic force divided by your current and your length. So to find out what is the unit of your flux density, or in other words, what is 1 Tesla, everything in this equation must be 1. All right. So now 1 Tesla is the magnetic flux density normal or perpendicular to a long straight wire carrying a current of 1 amp that produces a force per unit length of 1 Newton per meter. All right. If you then move on to part B, you have a magnet that produces a uniform magnetic field of flux density B in the space between its poles. A rigid copper wire carrying a current is balanced on a pivot, which is this one here. Part PQLM of the wire is between the poles of the magnet, which is actually this section right over here, as illustrated in the figure. The wire is balanced horizontally by means of a small weight W. So based on what I've explained earlier, what is probably happening right now is that you're having some sort of magnetic force downwards, which causes a counterclockwise movement like this. So what you're going to do now is that you're going to apply some sort of weight at the other end here so that you have a clockwise moment to balance off the moment caused by the magnetic force. Then in the next page, you have a close-up of the diagram. The section of wire between the poles of the magnet is shown in the diagram below. For the first part, explain why section QL of the wire gives rise to a moment about the pivot. And then for the second part, Y sections PQ and LM of the wire do not affect the equilibrium of the wire. So let's just try to draw out the directions of the current through the wire right now. Based on the diagram that we have from before, you notice that your current is actually going like this before going back the other way. So right now, we want to draw the direction of the currents over this side here for the section of the wire that's inside the magnetic field. So right now, what we should have would be something like this. We have our current going down here, and then going over here, and finally over here. And then because we already know the polarity of the poles of magnet, we could also likewise say that our magnetic field is going to be acting towards the right. So right now we want to draw out the magnetic force acting on each individual section of wire inside the magnetic field. So right now, if I'm talking about for section PQ, since my current direction is going downwards, and then my magnetic field is going towards the right, like this, if I were to apply Fleming's left-hand rule again, where my thumb represents the magnetic force, my index finger represents my magnetic field, and finally my middle finger represents my current, I would be able to determine that my magnetic force will actually be acting in this particular direction. Okay? And then if I move on to section QL, what I'll have would be something like this now. My current is going in this direction, but my magnetic field is going in this direction here. So this is my B, and then this one is my current. So according to Fleming's left-hand rule, my magnetic force would be acting downwards. Okay, and then for the last section here, for section LM, my current direction is going upwards. My magnetic field is going towards the right. If I use Fleming's left-hand rule now, I ought to be able to work out my magnetic force as being in this direction. Okay, so these are all the respective forces acting on the sections of wire. So now when you look at the diagram itself, the magnetic forces acting on the sections of wire inside the field will be indicated over here. Now, specifically, if you look at the directions of the magnetic force on sections PQ and LM, you could say that they are, number one, equal and opposite to each other. And then number two, they are acting horizontally along the same line. Okay. And then as for the last force here on section QL, you could say that it's actually just a vertically acting force. Okay. So now, if you were then to look at the entire diagram, say from this view here, if I redraw the entire diagram from the front, giving me a fully 2D view, it looks like this right now. This part here is my pivot, and then this part here is my wire. Okay. The magnetic force on section QL will be over here. This one is acting vertically. And then the magnetic force on sections PQ and LM will be right over here. This is magnetic force on sections PQ as well as magnetic force on section LM. These are horizontal forces. Okay, so when you just look at it like this, you can really see that the force on sections QL will actually cause a moment. Because this part here being my pivot, I already can see a perpendicular distance between the force and the pivot itself. This part here being my perpendicular distance. But then when I look at the forces on sections PQ and LM, the forces are actually horizontal. There's no perpendicular distance that you can see between the forces and the pivot itself. These forces here do not cause moment since there is no perpendicular distance. The fact that there are horizontal forces in the first place will already tell you that there's no perpendicular distance that you can consider. All right. So now if you look through the actual question itself under part 1, where you're supposed to explain why section QL of the wire gives rise to a moment about the pivot, you could explain it in this manner. Current in wire QL gives rise to a force that is perpendicular to the magnetic field. The force on wire QL is vertical and does not act through the pivot. Thus, a moment will be produced since there is a perpendicular distance between the force and the pivot. All right. And then as for part 2, why is it that sections PQ and LM of the wire do not affect the equilibrium of the wire? Now, when you're talking about equilibrium, if you recall what you've learned under AS before this, equilibrium was actually defined under 2 specific conditions, where they first tell you that there is no resultant force, and then the second condition was that there's no resultant moment. So you want to relate why the forces on sections PQ and LM do not affect the equilibrium of the wire based on these 2 criteria here. Now, remember just now I told you that forces on PQ and LM were actually equal and opposite. That would have directly related to this fact here that there are not going to be any resultant force. And then at the same time, I also say that they were acting horizontally along the same line. So because they were acting horizontally along the same line, there's no perpendicular distance between the forces and the pivot. This will in turn also mean that you have no resultant moment. So now when you want to write out your answer, you could write it in this way, where for the first one, you say that the forces act through the same horizontal line. This one means that there is no resultant moment. And then for the second answer, you could say that the forces are equal in magnitude but opposite in direction. This one would have told you that there is no resultant force. All right, then let's move on to the next part of your question. In part C, section QL of the wire has a length of 0.85 centimeter. The perpendicular distance of QL from the pivot is 5.6 centimeter. When the current in the wire is changed by 1.2 amps, W, which is the weight, is moved a distance of 2.6 centimeter along the wire in order to restore equilibrium. The mass of W is 1.3 times 10 power minus 4 kg. In part 1, show that the change in moment of W about the pivot is 3.3 times 10 power minus 5 Newton meter. So what you are supposed to find here is the change in moment caused by W. All right. So remember just now that when you were trying to balance the wire so that it remains horizontal, you actually added another separate weight on the other end of the wire. You added a weight W over this end here so that you have a clockwise moment. The magnetic force QL in the first place was actually already causing a counterclockwise moment here. So you needed to add another weight at the other end of the wire in order to balance the moment so that your wire remains horizontal. So here, the question mentioned that they actually changed the current in the wire by this amount. This is the change in your current, okay? Not really the current itself, but rather the change in the current. So when you change the current, by right, you're going to change the magnetic force, which in turn changes the moment exerted by your magnetic force. So your weight here, you did not really change the weight, but rather you change the distance so that the moment caused by the weight change correspondingly to balance the change in moment caused by your magnetic force. Now, since the question is asking you about the change in moment, let's look at how moment is defined in the first place. Moment is defined as the product of force and the perpendicular distance between the force and the pivot. So this is how moment was defined in the first place. So from looking at this equation, if you're talking about the change in moment, it could have come about from a few ways. Firstly, if you're talking about change in moment, it could be that the force has changed, but the perpendicular distance remained the same. Or it could also be that the force remains the same, but the perpendicular distance was the one that has changed here. Or it could be that both force and your distance change at the same time. So based on what the question mentioned here to you, they didn't really change the weight. The weight W is still the same. What they did change was merely the perpendicular distance. So you're really looking at the second case over here, where force remained the same, but the perpendicular distance was changed. So the first equation is out, and the third equation is out. So you would want to use the second equation for your question over here. So if you now look at the workings, I already wrote here moment is force times perpendicular distance, such that the change in moment is actually just the weight times the change in perpendicular distance. So now my change in moment is my weight mg multiplied with the change in perpendicular distance. The mass of the weight used was 1.3 times 10 power minus 4 multiplied with the gravitational acceleration, and then multiply with the change in distance of 2.6 centimeter. Don't forget to change out the centimeter to meter. Eventually, you will get the change in moment as 3.32 times 10 power minus 5 Newton meter. So round it up to 2 SF, you will get 3.3 times 10 power minus 5 Newton meter. So this is now shown. Now for the last part of your question, use the information in part 1 to determine the magnetic flux density B between the poles of the magnet. We know that the wire is in equilibrium, so that it remains horizontal. If we consider the equilibrium of the wire in terms of the moments only, we could say that the counterclockwise moment caused by the magnet would be equals to the clockwise moment caused by the weights. If you look at the question, they mention about changes in distance and then changes in your current. So rather than looking at your equilibrium in terms of the moments like this, it might have been better to consider the equilibrium in terms of the changes in moments, where instead of expressing the equation like this, you express them in terms of changes in moment, so that your equation becomes change in counterclockwise moment caused by the magnet equals to the change in clockwise moment caused by your weights. This would be the equation that you would want to use for your current question. So if you expand the equation further, you could say that the change in counterclockwise moment caused by your magnet is actually the same as the change in your magnetic force times the perpendicular distance between your magnetic force and your pivot. So in your case, it's actually this perpendicular distance between your magnetic force on section QL and your pivot. It is actually going to be 5.6 centimeter. This is your distance x. The 5.6 centimeter, you get it from over here. All right. And then as for the change in clockwise moment caused by your weight, it's actually your weight times the change in your perpendicular distance. You've actually found it over this part of your question here. So there's no need to repeat the calculation again. From here, if you're talking about the change in your magnetic force, the magnetic force is given by Fp equals to BIL. Now, since you're using the same magnet, your magnetic flux density will be the same. B is the same. And then since you're still using that same wire, specifically the same section QL of your wire, you could say that the length of your wire inside the magnetic field remains the same. B and L remains the same, but your current actually changes. So, but I changes. So that right now, if you want to consider the change in your magnetic force, it's really going to be the flux density multiplied with your change in current multiplied with the length of wire inside your field. So now, if you want to expand out your existing equation, this one would be B times change in current times with your length of wire inside the field, then times your perpendicular distance between your magnetic force and the pivot, and then equate it to the change in clockwise moment caused by your weights. So right now, your working would actually be the one that is being shown here. And then from there, all you need to do is just to sub in your values. You want to find out the magnetic flux density. Your change in current is actually 1.2 amps. Your length of wire inside the field is actually 0.85 centimeter. Remember to change it out from centimeter. So now it becomes 0.085 meter. And then after that, when you're talking about the perpendicular distance between your magnetic force and your wire, it should be 5.6 centimeter. Again, remember to change it out from centimeter. So now it becomes 0.056 meter. And then lastly, your change in clockwise moment caused by your weight is already found from the question above. Then from there, you can now find out your flux density as 5.78 times 10 power minus 3 Tesla. All right, so that should be it for this question. And now for our last question, let's have a look at page 58. This would be November 2021 P41. So in our current question, you are supposed to define the Tesla. We already know that the Tesla is actually the unit of magnetic flux density. So that when you're talking about magnetic flux density, the equation was actually FB equals to BIL, provided that the wire is perpendicular to your B field. Then from here, flux density will be equals to your magnetic force divided by your current as well as your length. So if you were to have 1 Tesla here, everything else must be 1. Your magnetic force must be 1, your current must be 1, and your length must be 1. So if you were now to define your Tesla, it is actually the magnetic flux density normal or perpendicular to a long straight wire carrying a current of 1 amp that produces a force per unit length of 1 Newton per meter. This is actually following what you are seeing right over here. Okay. And then now if you move on to part B, you have a stiff metal wire that is used to form a rectangular frame measuring 8 cm by 6 cm. The frame is open at the top and is suspended from a sensitive Newton meter as shown in the figure below. The open ends of the frame are connected to a power supply so that there is a current of 5 amps in the frame in the direction as indicated in the figure above. The frame is slowly lowered into a uniform magnetic field of flux density B so that all of side PQ is inside the field. The magnetic field lines are horizontal and are at an angle of 50 degrees to PQ. From there, they also did mention that when side PQ of the frame first enters the magnetic field, the reading on the Newton meter changes by 1 millinewton. So right now, when you look at the diagram, the rectangular section of your wire is this part here. They say that there is current flowing through your wire. There is 5 amp going in this direction, as well as in this direction. They mentioned specifically that this section of wire, PQ, is lowered into a magnetic field and is at an angle to your magnetic field. If you were to view your wire from above, this is what you would expect to see. Your section of wire PQ is right over here, and then your magnetic field is over here, making an angle of 50 degrees to the wire itself. Okay, so what does the question want you to do right now? If you move on to the first part of your question, they ask you to first determine the magnetic flux density B in millitesla. So look at the diagram here. So from the second diagram that you have here, you can see that the direction of your magnetic field is actually in this particular direction. This is the direction of your B, and it's actually making an angle of 50 degrees to the horizontal. You can see that if this is 50 degrees, this one must also be 50 degrees. All right. And from here, what you want to do is that you want to resolve that magnetic flux density into 2 perpendicular directions. You could easily resolve it into a horizontal component as well as a vertical component. If you look at the horizontal component, it being adjacent to your angle would mean that this one is actually B cos 50 degrees. And then the other one would have been B sine 50 degrees. So right now, let's consider the direction of your current flow. if you look at the diagram above, current was flowing like this, and like this. You're interested in the current direction in section PQ. You can see from here it's actually moving towards the right. So if you were to go and indicate out the current direction in your second diagram, this is the direction of your current flow. Okay, so right now there's supposed to be a magnetic force that is produced. Which one is actually causing your magnetic force to be produced? Now, if you look at the horizontal portion here, your current is actually parallel to your magnetic field. So this one here does not produce your magnetic force. Okay, and then when you look at the other component of the magnetic field over here, you can actually see that it forms a 90-degree angle with your current. So you can say that B sine 50 is actually what produces your magnetic force. So you want to consider the interaction between B sine 50 and your current that is going towards the right. You would have to use your Fleming's left-hand rule again, FLR, where here your thumb, your middle finger, and your index finger are used. Your thumb represents your magnetic force, your index finger represents your magnetic field, and then your middle finger represents your current. So right now, you want to apply Fleming's left-hand rule to B sine theta and the current. Work out what is the direction of your magnetic force. If you do that, you will be able to work out that the direction of your magnetic force is actually coming out of the plane of your paper. Here, your magnetic force is coming out of plane of the paper. So if you want to have a better view of what the direction is, you look at the diagram above, your magnetic force is actually going upwards in this direction here. Okay, so this is the direction of your magnetic force. All right. Now, this magnetic force is actually opposing the weight of the wire acting downwards. When you then consider the effects of these two forces, it should cause the reading on your Newton meter to decrease. The question did mention that the reading on your Newton meter changed by 1 millinewton. So here, the reading actually decreased by 1 millinewton. Okay. Now, the reading having decreased by 1 millinewton came about because you suddenly have a magnetic force arising. So it would be correct to say that the change in your force that you had is actually the magnitude of the magnetic force itself. Right now, in the first part of the question, if you remember, you're supposed to find out what is your magnetic flux density B. So you want to relate your magnetic flux density B and your magnetic force. If you look at the second diagram, the direction of your magnetic field is in this direction, but the direction of your current, or rather the wire, is actually at a certain angle to your magnetic field. When it comes to the force acting on a wire, there are actually two equations. The first one was FB equals to BIL. This is only if wire is perpendicular to your magnetic field. And then the second equation would have been FB equals to BIL sine theta. This one will be used if your wire is at an angle to your magnetic field. So you would want to use the second equation now, since you can see that your magnetic field is at an angle to your wire. So you know the magnitude of your magnetic force, you know the magnitude of your current, you know the length of the wire inside the field, you know the angle. So you can now find out what is your flux density. Now, if you look at the workings inside the work solutions, you would use equation FB equals to BIL sine theta. Your magnetic force, as discussed, was actually 1 millinewton, so it's 1 times 10 power minus 3, equate it to your flux density, multiply with your current of 5 amps, and then multiply with the length of your wire inside the magnetic field, which is actually the length of section PQ. The length of section PQ, you can actually see that it's actually 6 centimeter. Okay, so use that value, 6 centimeter, change it out from centimeter to meter, and then your angle is going to be 50 degrees, so it's sine 50. So finally, your answer will be B equals to 4.35 times 10 power minus 3 Tesla. Now you want to change your answer to millitesla, so all you just need to do is to divide by 10 power minus 3 to get the final answer as 4.35 millitesla. And then you move on to part 2, state with a reason whether the change in the reading on the Newton meter is an increase or a decrease. So right now, if you look back at the original diagram that I drew out for you, your magnetic force was actually acting upwards. So it's actually pushing up, opposing your weight. So by right, the reading must be decreasing. Okay, so how will you write your answer? You just write it in this manner here. You just say that the force on the wire is upwards from Fleming's left-hand rule, thus your reading decreases. Okay. So for the last part, the frame is lowered further so that the vertical side starts to enter the magnetic field. Suggest what effect this will have on the frame. So just to recap, the side view of the wire looks like this, with the current directions indicated. And then after that, the top view of the wire looks like this. Wire section PQ, which was this one, if viewed from the top, you see that the magnetic field forms an angle to that section. Okay, so earlier, just now, we already established that the magnetic force while acting on section wire PQ was actually upwards. So now we're interested to find out the magnetic force acting on the vertical sections of your wire. So it'll be easier to work that out by looking at the top view. If you look at the first vertical side, which is this one, you could say that the current is going into the plane of the paper when viewed from the top. And then when you look at the second vertical side here, you could say that the current is going out of the plane of the paper when viewed from the top. Okay, so from here, if you already know the direction of the current as well as the direction of the magnetic field, you by right ought to be able to work out what is the direction of the magnetic force by using Fleming's left-hand rule. So now, if you use Fleming's left-hand rule to work out the direction of the magnetic force on the vertical sections of the wire, for the first section, which is basically this one here, you will be able to work out that the magnetic force is going to be somewhere in this direction, making an angle of 90 degrees with your magnetic field. And then after that, when you move on to the second section of your wire, which is this one, you use Fleming's left-hand rule again, you will be able to work out that the direction of your magnetic force ought to be in this direction. Again, it is making a 90-degree angle with your magnetic field. So look at your forces right now that have arisen on the section of your wire. They are going to cause a moment in the same direction. You see that this force here is going to cause a moment counterclockwise. This one is also going to cause a moment counterclockwise. So they are both in the same direction. You could say that overall, there is a resultant moment produced by the magnetic force acting on vertical sections of the wire. Okay, so now you can see that there's a resultant moment counterclockwise caused by the forces acting on the vertical sides of the wire. Therefore, the wire rotates counterclockwise. Okay, does it continue to rotate counterclockwise indefinitely? It eventually will stop rotating. So that's what we are interested to find out next. So if the wire frame continues rotating counterclockwise, where would it actually stop? let's redraw the pattern of your magnetic field that is at an angle to your horizontal. So assume that this point in the center here is actually your pivot. If the wire rotates about your pivot, it will eventually stop rotating when the wire is actually perpendicular to your magnetic field. This one is your magnetic field. This one is your wire PQ. Okay, so if it continues to rotate counterclockwise from this initial direction indicated here, you will notice that your current over this side is actually coming out of the plane of the paper, and your current over this side is going into the plane of the paper. So now if you use Fleming's left-hand rule to work out the direction of your magnetic force, you will now notice that your magnetic force direction for this end here is in this direction, and for the other end is going to be in this direction. This would be your magnetic forces right now, acting on the vertical sides of your wire. So notice that they are going to be acting along the same line here. So it also passes through your pivot at the same time. There's no perpendicular distance to consider. So here, there is no moment produced, therefore no rotation anymore. So you now want to word your answer. You just say something like this. The frame will rotate so that PQ becomes perpendicular to the field. Okay, so this should be the last question for now. All right.